Hello everyone, my name is Stu Adler. For the next 10 weeks, I'll be your host for what I hope you'll find is an interesting and useful introductory lecture series on the subject of thermodynamics. Although this series is tailored to undergraduates studying chemical engineering, thermodynamics is an incredibly fascinating and widespread subject that permeates nearly all disciplines of science and engineering. Today I thought we should begin by discussing a little bit about what thermodynamics is and why we as chemical engineers spend so much time studying it. Historically, thermodynamics has gained a reputation for being kind of a difficult subject, inspiring cartoons like this one. Student is on the couch describing his anxiety dreams to his psychiatrist. "It's a recurring nightmare, Doc. I'm in this class where calculus is the easy part." The funny thing about this cartoon is that it's actually a pretty accurate characterization of thermodynamics, but not for the reasons you might fear. Most of the day-to-day mathematical aspects of undergraduate thermo are fairly straightforward when broken down piece by piece. The harder part, in my opinion, is fully grasping the big picture of how these procedures fit in, and how the various parts of thermodynamics fit together, and how they apply to engineering. When I first took thermo in the 1980s, it was taught in a way that required a lot of suspension of disbelief. In other words, trust me, learn these various skills and separate bits and pieces of knowledge, and someday you'll see how they all fit together. For me, that assembly process didn't really happen the first time. It took multiple exposures to thermodynamics in a variety of different contexts before the light bulb went off over my head. So part of my goal with this course, starting with this first episode, is to save you some of that grief and help frame what thermodynamics really is and why you should care about it as a chemical engineer. I think a good place to start this discussion is to first consider what engineering is. When lay people think of engineering, they often focus on the end goal or product of engineering, a machine, a structure, a substance, a system that makes our lives better or easier in some way. But these are all nouns describing the end goal or product of engineering. The act of engineering itself, which you're training to do, is a verb, to engineer. So what are we actually doing when we engineer something? And what is the first step we take in our technical approach to any engineering problem? One way to illustrate the relevance of this question is this painting by the late 19th century artist Hermann Simon. The painting shows the struggles of two farmers trying to get a mule onto a boat. They're pulling and pushing and straining to get this mule to cooperate, but the mule has its own ideas and is clearly having none of it. What this painting nicely illustrates is that nature often has its own motivations, and trying to come up with solutions that ignore or go against these motivations is basically a non-starter. In contrast, here's a recent photo illustrating one person's engineering solution to this same problem. Rather than battling the mule, this fellow has come up with a simple, practical device that directs the mule's natural motivations in a useful way. This, in a nutshell, is what the act of engineering as a verb is really all about. The engineered device itself is just a stick with a carrot tied to it, so building it wasn't really the difficult part of solving the problem. The engineering challenge was to develop a deeper understanding of the mule's motivations and limitations. For example, for this device to work properly, the mule has to like carrots well enough to try to walk forward to grab it, but it has to be dumb enough not to realize that the carrot will just move further away. Understanding these unique characteristics of the mule was a key first step in engineering a workable solution. So too with chemical engineering. Often the design of chemical process equipment is straightforward and involves well-established procedures. The real engineering challenge is understanding chemical systems, their motivations and limitations well enough to develop creative solutions that meet technical, economic, environmental, and societal constraints. As with the mule, we need some kind of framework for understanding the motivations and limitations of chemical systems. This, in essence, is what thermodynamics is about. Ironically, most textbooks in thermodynamics never actually define the term thermodynamics, leaving students to infer its definition from the totality of its content. I think that's a mistake, so let's start with a definition. Thermodynamics, a theoretical framework for understanding and predicting how groups of molecules will behave spontaneously. Along with this definition, I'd also like to point out several aspects of thermodynamics as a theory that narrow and focus this definition a bit more. One is that thermodynamics focuses primarily on the aggregate behavior of groups of molecules, not on the specific actions of individual molecules. Of course, the theory does incorporate information about molecular properties and structure, but this is aimed at understanding how groups of molecules will respond in an average way, not predicting what any one particular molecule will do. Another feature of thermodynamics is that it is focused on the behavior of molecules at equilibrium, not on the pathway or rate at which molecules reach equilibrium. For example, imagine we put a bunch of molecules in a box of fixed volume and allow those molecules to reach equilibrium with each other at 20 degrees C. By allow, I mean we give the molecules enough time to stabilize in some average arrangement when viewed macroscopically. Of course, at 20 degrees, the individual molecules will be moving around rapidly, even at equilibrium. But given enough time, any macroscopic properties that depend on molecular arrangement, such as pressure, density, etc., will eventually stop changing. The question that thermodynamics seeks to address is how the molecules will be arranged on average in the box at this point. It does not address the larger question of how the molecules will reach this state of equilibrium or how long it will take to get there. So why is this useful? Well, first, we're often interested in manipulating atoms or molecules into a particular arrangement. Sometimes that arrangement is an equilibrium arrangement. In this case, thermodynamics helps us predict the conditions under which our desired target will form spontaneously. It is amazing, almost unbelievable, how many unit operations in a typical chemical process, for example, most physical and chemical separations, many chemical reactions, basically involve mixing a bunch of stuff together and giving them a place to come to equilibrium. The molecules do the rest, all by themselves. Our job is simply to arrange the necessary conditions and then get out of the way. Sometimes this can be as simple as understanding what phases of matter will form under a defined set of conditions. Think about the humble and familiar molecule H2O. On its own, it's a pretty simple molecule from the standpoint of stoichiometry and structure. But when it gets together with its buddies, it can take a wide range of forms with interesting properties, depending on the conditions. It can be a gas. It can form an ordered solid with unusually low density due to its hydrogen bonding. The same hydrogen bonding also allows H2O to exist as a liquid at remarkably high temperatures, despite its small size, which is unmatched in its ability to dissolve other substances in it. So which of these forms will H2O take under a given set of conditions? And what factors determine this form? Although this is a very simple example, similar questions arise in more complex molecular systems, such as multi-component mixtures involving two or more phases, conformations of proteins in biology, self-assembly of macromolecules at an interface, adsorption of molecules on a surface. These turn out to be problems with very similar features when viewed through the lens of thermodynamics. A second goal of thermodynamics is to help us predict what will happen to systems that are out of equilibrium. Even when process steps don't require a detailed understanding of rates, we often still need to understand and predict the direction and extent that systems of molecules will evolve when they're placed or held away from equilibrium. So for example, if we take ice at minus 10 degrees C and water at 70 degrees C and mix them, what phases and conditions will prevail when the H2O comes to equilibrium? And what does this tell us about the steps that will be relevant in reaching this equilibrium? In addition, even though predicting rates falls outside the purview of thermodynamic theory, thermo provides a basis and background for formulating rate laws in chemical kinetics and heat, mass, and momentum transport. Thus, thermodynamics, just like heat and material balances, provides a foundation for many other subjects studied by chemical engineers. To help illustrate a bit better where we're headed, I'd like to introduce you to a few simple systems that illustrate the types of problems we'll be studying over the course of a quarter. The first is the classic problem of phase equilibria. This problem is of special significance to chemical engineers as it forms the basis for many separation and extraction processes, so much so that we have almost an entire course devoted to it, which you'll take next quarter. Shown here is a sealed bottle containing a mixture of H2O and isopropanol, a 3-carbon alcohol. Some may recognize this mixture. It's sold in drugstores as rubbing alcohol, commonly used as a disinfectant. The mixture also contains a small amount of a green hydrophobic but alcohol-soluble dye to help us see what's going on. As you can see, under ambient temperature conditions, these molecules appear to mix and remain a single-phase liquid. Agitating the bottle does not disrupt this mixture in any way, and no matter how long we wait, the mixture remains stable as a single-phase liquid. In contrast, let's now look at a mixture of H2O and butanol, a 4-carbon alcohol having similar chemical structure as isopropanol. Even after violently shaking and mixing the two principal molecules together, we see that over the course of a few minutes, the system separates into two separate liquid phases. Since alcohol is less dense than water, we can surmise that the upper phase contains most of the alcohol, while the lower phase contains most of the water. This is consistent with the distribution of the hydrophobic dye, which is relatively insoluble in water, but is soluble in alcohol. In fact, if we were in need of a process for removing trace amounts of this dye or some other similar molecule from water, this might be a nice way of doing it. So why does this phase separation occur, and why does switching from a 3-carbon to a 4-carbon alcohol make such a profound and discontinuous change in system behavior? As a third case, let's return now to our original mixture of isopropanol and water, but now add a third molecular component, salt. We can see that the mixture that was stable originally as a single-phase liquid is no longer stable and separates into two liquid phases. Why does adding salt alter the phase stability? These and related questions of phase equilibrium are at the core of thermodynamics, and something we'll work toward understanding by the end of the quarter. Another problem addressed by thermodynamics is the interconversion of different forms of energy. For example, here we have a cup of coffee, which due to its elevated temperature is out of equilibrium with its environment. If left to its own devices, it will evolve heat until it cools and reaches equilibrium with the ambient temperature. As with the mule, we might like to harness this natural tendency in some way to do something useful. For example, maybe we could extract mechanical work. To that end, let's introduce a device called a Stirling engine, which uses the natural expansion and contraction of air as it is heated and cooled to drive the motion of a flywheel. The engine contains a volume of air exposed sequentially to two metal plates, one of which is exposed to the hot coffee, the other exposed to the cool air in the room. As the flywheel rotates, it moves a foam displacer, causing the air to move back and forth between the two plates. When the air is in contact with a hot plate, it expands, displacing a small piston, driving the flywheel. When the air is in contact with a cold plate, it contracts, pulling the piston back to its original position, which also moves the displacer back to its original position, and so forth in a periodic cycle. The net effect is that movement of heat from the coffee to the environment is partially converted to mechanical work. How much power can we get out of this process? Is there a limit to the engine efficiency that goes beyond the conservation of energy? How does the work extracted relate to the properties of air and the geometry of the engine? This and other questions of energy conversion and process efficiency are also at the core of thermodynamics, and something we'll explore and seek answers to by the end of the quarter. At first glance, this example of a Stirling engine might seem like a very different problem than the question of phase equilibrium, which we just examined previously. However, it turns out they are incredibly closely related. As we'll see, this connection is the question of how groups of molecules at equilibrium transform when subject to changes in energy content. This question was first addressed by workers in the 19th century who were interested in building better steam engines and needed to understand and predict transformations of H2O. Hence the word thermodynamics, which is a reference to the Greek thermos, which means heat, and dynamis, which means power or force. So why is the energy content of the substance tied to its equilibrium behavior? This is really the essential question we need to address over the course of the quarter. To get us started and perhaps gain some initial insight into this question, I'd like to present a third and final example related to the problem of food production. Shown here is a recent map of worldwide use of nitrogen-based agricultural fertilizers. As you can see, regions of higher fertilizer use tend to align with first world nations or countries with high population density, such as the US, Europe, China, and India. This map illustrates a well-established correlation between a country's use of industrial fertilizers and its GDP, a rough measure of that country's wealth. In fact, as measured by tonnage, the principal role of the chemical industry is supporting food production, as the top two most produced chemicals in the world, sulfuric acid and nitrogen, are used primarily for making fertilizer. So how are fertilizers made? A major step forward came in 1908 in Germany when Fritz Haber and Karl Bosch came up with a scalable industrial process for making ammonia, the principal feedstock for nitrogen-based fertilizers. Their process is based on the reaction of gaseous hydrogen and nitrogen to form gaseous ammonia. If we're designing a reactor for this, what do we need to think about? Part of the problem, of course, is stoichiometry. Balancing a reaction statement so as to obey an atomic balance, it implies that if we feed a 3-to-1 ratio of H2 to N2, we will produce 2 ammonia molecules for every 4 molecules of reactant. However, beyond this, what can we say about whether this reaction will actually happen? And if it does happen, how fast will it occur? Part of this question was answered by Fritz Haber, who discovered experimentally that if the gases are heated to 350 to 550 degrees C and then exposed to an iron catalyst, these 3 molecules would readily interconvert between ammonia and a 3-to-1 ratio of H2 and N2. At this point, we might ask whether it's possible to develop a catalyst that only helps the forward reaction, leading to complete conversion of the reactants to ammonia. Unfortunately, this violates a basic principle of thermodynamics known as microscopic reversibility, something we'll discuss in a bit more depth later. But one consequence of this principle is that a catalyst that helps a reaction in one direction must also help the reverse reaction. The net result is that the catalyst cannot influence the desired equilibrium state of the molecules. It can only help the reacting molecules reach that equilibrium more easily. Having solved the kinetics problem of getting the molecules to react, the next question facing Haber and Bosch was understanding how much ammonia will form at equilibrium under a given set of conditions. What they found experimentally was that as the temperature is increased, which favors faster kinetics, the equilibrium concentration of ammonia they produced became much less. Why is this? To address this question, let's examine a bit more closely 2 issues that we might expect to influence the equilibrium of this reaction. The first is the energetics of the reaction. Like the air in the Stirling engine, we might expect the equilibrium behavior of reacting molecules to depend on how they transform upon changes in energy content. Indeed, consider the following similar reaction involving the reaction of H2 and O2 to form H2O. You might recognize this reaction as extremely exothermic, a reaction that once initiated will violently go to 100% completion and release a lot of thermal energy. Indeed, if we look at the standard enthalpy of reaction, which is one measure of this exothermicity, we see that it is extremely negative, meaning it releases a lot of energy. We might expect intuitively that reactions that release a lot of energy will favor products at equilibrium. This intuition is correct for reasons we'll discuss in more depth later. This being the case, if we compare the enthalpy of reaction for the ammonia reaction, we see that it is much less exothermic than the water reaction. In fact, it's quite close to being thermally neutral, meaning that energetics do not strongly favor formation of ammonia versus H2 and N2. This raises the second issue we might expect to influence the reaction: probability. Imagine for a second that energetics didn't matter, and the H and N atoms rearrange themselves randomly among the reactant and product molecules. What would happen? Well, if we compare the reactants, which total 4 molecules, to the products, which only have 2 molecules, we might expect there to be more ways to randomly arrange the atoms on the reactants. This implies that on average, we would expect to have more reactants than products. As we'll discuss in more depth later, one measure of how many different ways there are for a group of molecules to rearrange is a property called entropy. Looking at the standard entropy of reaction, we can see that it is quite negative, supporting our intuition that the reactants have a higher probability than products, assuming neutral energetics. Recognizing these 2 competing factors of energetics and probability, Haber and Bosch came up with a solution. Some of you might recall Le Chatelier's principle, which states that as you increase the concentration of a reactant or product, it will drive the reaction equilibrium to the right or left, respectively. Since in this case the reactant molecules outnumber the product molecules, an increase in overall concentration will drive the reaction to the right. As we'll see, this effect is really a manifestation of entropy. By increasing the pressure of the gas mixture to about 10 bar, Haber and Bosch were able to alter the entropy of reactions sufficiently to better favor the products. Using tools you'll learn in this course, we can calculate the equilibrium conversion of ammonia under various pressure and temperature conditions. We can express the results as a contour plot of fractional conversion F as a function of temperature and pressure. What this plot shows is that at 1 atmosphere pressure, high fractional conversion can only be achieved at low temperature, where the reactants are unable to reach equilibrium kinetically. If we add a catalyst and raise the temperature, we can get the molecules to react fast enough, but conversion is less than 10%. But by also raising the pressure to 10 bar or so, we can get to 25% conversion. This conversion was high enough that Haber and Bosch could combine their reactor with a condenser to separate the ammonia and then recycle the H2 and N2. Speaking more generally, the energetic and probabilistic tendencies of molecules play a central role in all the examples I presented you with today. The essential benefit of thermodynamics is that it allows us to understand and predict the balance of these tendencies as embodied in the energy and entropy of the molecules. Over the course of this quarter, we'll revisit each of these examples in much more depth and really try to understand what's going on. At the same time, I hope to provide you with a useful set of general strategies and tools you can use to predict the equilibrium behavior in molecular systems.